Okay. Have uploaded the lecture notes for the chapter 10. Okay, chapter 10, there is a part 1 and part 2. Part 1 I have uploaded to you. Okay, part 2 I just uploaded to you today. Okay, you will have to download it. Okay, if you want to refer, you can download it now. Okay, I have something I want to discuss with all of you is about the class, our lecture and tutorial class next week. Okay, there will be some reschedule of your class, but I want to confirm with all of you before I reschedule. Okay, I have just shared a link. Okay, the link is a link to Google Classroom. Okay, if you want to go and download the lecture notes, you can uh, use the link to download. Okay. Uh, next week is week 14. Okay, we still have class on Monday and Wednesday. Okay, on Monday, there are 2 hours. Okay, 2 hours class. One is lecture, another one is tutorial. Okay, I want to ask all of you whether we can change the lecture class from 10:30 to 11:30 a.m. a.m. Means that our lecture class to reschedule to early uh, okay, after you consider, please let me know, is it okay? Okay, why is the reason I until what time? I estimate that the webinar will be around 1 hour to 1.5 hours. Okay, the time will clash with the lecture class at 10:30 until 11:30. So that's why I want to reschedule it to 8:30 until 9:30. It is quite early, okay, quite early, but I think most of us we can still make it. If we can, we still can make it. If just one day, okay, it is just one day. Only next Monday, okay. And then the tutorial, okay, the tutorial is from 11:30 to 12:30. Okay, tutorial class will maintain. Okay, this I will maintain. I will not do any reschedule. Okay, just the lecture class. Okay, I want to make it early. Uh, I want to confirm with you. If all of you okay with that, this the lecture class, okay, we will make it at 8:30 a.m. Can you all get me there? Okay, I need some of your respond, okay, to know whether okay or not. Okay, this one, okay, if okay, next week all of you have to wake up early, okay, and join the class. Okay, okay, you can consider first, okay, you can let me know later. Okay, another class, there is another class on Wednesday. Okay, Wednesday from 2 to 4 p.m. 2 to 4 p.m. Is a lecture class. Okay, I need to reschedule this lecture class to Thursday because Wednesday is a products. Okay, it's a products. I may not be able to have the lecture class because I will be busy with products. Okay, I want to reschedule to Thursday from 10 to 12. Okay, I have checked your timetable. Okay, all of you, you don't have any class that time on Thursday. So I will make it 10 to 12. This one should be no issue. Okay. Uh, this one is the last day. Okay, last day of our lecture class. Okay, I still have to make it because I need to give you some tips for your final exam. Okay. So please take note. Okay. Later I will re-announce again. Okay, to inform you of the replace class for Wednesday lecture class. Okay, and the Monday class just now I mentioned, if I didn't receive any response from all of you, I will assume that all of you are okay. Okay, maybe I will ask students in DK. How about three of you? Can try and make it or not? Lecture class. No problem.
Shouldn't be a problem, but just that I don't know for the since Miss asked them they didn't have response in the chat box. I think okay lah.
Okay. Not there is you all doesn't have anything in the mornings, right? Monday, no. Okay. So I will just make it to 8:30 to 9:30. No objection anymore. Mm. Okay. So this is confirmed. Okay. I asked your classmate and student in Google Meet also no response. So I will assume that all of you are okay. So our lecture class will be from 8:30 to 9:30. Tutorial still maintained. Okay. And Wednesday change to Thursday. Okay. This change of time of the lecture class, I will announce in Google Classroom. Okay. Just in case. Okay. So now I will start the class. Okay. Eh, then just now when I discuss the time, is it can hear my voice?
Yeah, yeah.
Can. Then when I mute my mic just now. Ayo, what? Yeah. Okay. Slideshow. Okay, in previous class, I have covered some other method, okay, that can use to reduce the power dissipations. In low power design, the power dissipation is quite critical. Okay, it's quite critical. There are several approach, okay, and reductions method that we can apply at different level. Okay, previously I have mentioned before. Okay, the level there are different level. I go back to the slides, okay, to revise back what I have covered in the previous class. Okay, so this is the level. There are 4 level. This level, at different level, there are different methods for power consumptions reductions. Okay, and then also I have covered what is the motivations to achieve low power design. Okay, there is the slide given here. Okay, you can refer. This is the motivations. Okay, and then some other parameters that are important. Okay, when we want to consider the reductions of power consumptions. Okay, what are the parameters that we can use uh, to reduce the power consumptions? For example, okay, to reduce the power consumptions, we can actually reduce the supplies voltage. Okay, power supply voltage. Okay, VDD. Okay, we also can reduce the threshold voltage. Okay, and then there are some trade-off I also mentioned. Okay, when we reduce the power supplies voltage, the power consumptions will also reduce, but at the same time, the delay will increase. Okay, I have mentioned this in one of the slide. Okay, this is important. Okay, all of these are important. You need to understand what is the threshold. Okay, so then another parameter is the clock frequency. Okay, clock frequency is the F. Okay, clock frequency can also reduce the power consumptions, but if we reduce it, we have to consider the overall system performance. Okay, so this is what I have covered in the previous class. All these are important. Okay, today I will continue with this slide. Okay, it is about the influence of voltage scaling on power and delay. Okay, the voltage scaling here means by the scaling of the supplies voltage. Okay, and also the threshold voltage. But in this slide, it means the supplies voltage. Okay, what is the effect of rescaling the voltage on the power and delay? Okay, let's see the statements here in the slide. Okay, the reductions of power supplies voltage significantly reduce the dynamic power dissipations. The inevitable design trade-off is the increase of delay. This can be seen easily by examining the following propagations delay expressions for the CMOS inverter circuit. Two expressions are given here. Okay, these two expressions are the propagations delay expressions. Okay, from high to low propagations delay and low to high propagations delay. Okay, remember that this propagations delay is refers to the high and low at the output. Okay, and then the formula here you see that the parameters that can influence the propagations delay are the VDD, the supplies voltage, okay, and the threshold voltage VT. Okay, and also there is CL. CL is the load capacitance. This is C load. Okay, C load is the load capacitance. Okay, and the rest here you see the parameters is the supply voltage and threshold voltage. So it means that the supply voltage can affect the propagations delay. If the power supply's voltage is scaled down, while all other parameters are kept constant, the propagation's delay time would increase. Figure 11.9 shows the normalized variations of the delay as a function of VDD, where the threshold voltages of the NMOS and PMOS transistor are VT equals to 0.8 volt. Okay, this VT is the threshold voltage for NMOS. Okay, its threshold voltage is a 0.8 volt, and the threshold voltage for the PMOS is negative 0.8 volt respectively. Okay, so you can see the threshold voltage for NMOS and PMOS, the magnitude are the same. Okay, except that the sign, you see the sign, one is negative, another one is positive. Okay, uh, this can be explained. Okay, PMOS and NMOS they work inversely. Okay, so threshold voltage also must be the value can be the same, but the value cannot be the same high. Okay, one must low, one must high. Okay, the normalized variations of the average switching power dissipations as a function of the power supply voltage is also shown on the same plot. Okay, this is a graph. Okay, you have to understand what is meant by the graph here. Okay, it is plot with a delay. Okay, the y-axis is the delay on the left side. Okay, and on the right side is the normalized power dissipations. Okay, and the x-axis is the power supply voltage. Okay, this graph shows that the supply voltage is as low as 1 until 7 volt. Okay, and the line here shows that if the power supply voltage is increased, okay, then what will happen? Okay, the line shows that the power dissipations will also increase because it is increased proportionally. Okay, it is increased proportionally. And then the delay, you see the curve here. Okay, when the supply voltage is increased, power dissipations increase, the delay will decrease. Okay, delay will decrease. Okay, if you see this at this point, okay, you can see at this point 6 when the VDD is 6 volt. Okay, the delay is very small and power dissipation is very high. Okay, but when the power supply voltage is very low, okay, low here means the VDD is about 1.5. Okay, 1.5, you see here the power dissipation is low. Okay, and the delay is high. Okay, so when we want to reduce the VDD, we cannot simply reduce it as low as possible. No. Okay, we have to consider the delay as well. So the reductions must be appropriate. Okay, we have to use the appropriate value. Okay, so that we can achieve not high delay and also not high power dissipations. The dependence of circuit speed on the power supply's voltage may also influence the relationship between the dynamic power dissipations and the supply's voltage. If the circuit is always operated at the maximum frequency allowed by its propagation delay, the numbers of switching events per unit time will drop as the propagation delay becomes larger with the reductions of the power supply's voltage. Okay, so the statements here is about the switching event. Okay, the speed. Okay, switching speed. Uh, the in the previous slide, okay, it shows the reductions of the power supplies will affect the delay. Okay, and also the switching speed. Okay, the numbers of the switching event will also drop. Okay, when the delay become larger. Okay, so this is another parameters that will also influence by the power supply's voltage. The net result is that the dependence of switching power dissipations on the power supply's voltage becomes stronger. The propagations delay expressions 11.11 shows that the negative effect of reducing the power supply's voltage upon delay can be compensated for if the threshold voltage of the transistor is scaled down accordingly. However, this approach is limited because the threshold voltage may not be scaled to some extent as the supply voltage. Okay, the expressions for 11.11 is the expressions that I showed you just now, the two expressions. Okay, when scaled linearly, reduced threshold voltages allow the circuit to produce the same speed at a lower VDD. Okay, the threshold voltage we also can reduce. Okay, we also can reduce to achieve low power design. Okay, but the reduction also there is a trade-off. Okay, there is a trade-off. If we reduce the threshold voltage, the switching speed can improve. Okay, the switching speed can improve, but the power dissipations maybe will not be low. Okay, it will be high. Okay, why I say that because there are some other power dissipations due to linkage. Okay, about this I will further explain. Okay, later. Okay, so this all this you must understand. Okay, you must understand. You have to try understand if you cannot understand. Okay. Okay, another graph shown in figure 11.10, it shows the variations of the propagations delay of a CMOS inverter as a function of the power supply's voltage and for different threshold voltage value. Okay, you see the figure 11.10 here, a graph, also a graph plot with the normalized delay versus the power supply's voltage. Okay, and the line here indicate the use of different threshold voltage. Okay, VT is threshold voltage, and the values of the threshold voltage used is a 0.8 volt, 0.6, 0.4, and 0.2. Okay, and from this graph, what we can conclude? Okay, if we see at this point, okay, if you see at this point, okay, I take another point. Okay, I take this point, 2 volt. When VDD is 2 volt. Okay, when VDD is 2 volt, means the supply voltage is constant. Okay, supply voltage is constant, and the use of the threshold voltage here are different. Okay, when the threshold voltage value is different, you see the delay also different. Okay, higher threshold voltage will have higher delay. Okay, when the threshold voltage is reduced to 0.2 volt, the delay is smaller. Okay, a small delay. Okay. My tablet is quite sensitive. I'm sorry. Okay. This is delay. Okay, small delay. This is small delay. Okay, you can see from the graph here at 0.2 volt, the threshold voltage, the delay here is around 4 point something. Okay, 4.6, okay, or 4.7. Okay, and compared to this, when the threshold voltage is 0.8 volt, the delay is more than 12. Okay, so mean there is a large delay here. Okay, high delay. Okay, so when we want to consider the threshold voltage, okay, we have to consider the use of the threshold voltage. Okay, the value. What I mean is the selections of the values for threshold voltage. Okay, in a circuit where if we want to have a small delay, okay, a smaller threshold voltage is required. Okay, but at the same time, we need to make sure that the power consumption is not very high. Okay, uh, here I write here. Okay, small Vt, okay, will have high power dissipations. Okay, this power dissipations, we usually call it as uh, standby power dissipation. The standby power dissipations will be high. Okay, uh, and this is the disadvantages. Okay, you need to know this is the disadvantages. You need to record down. Okay, and the advantages is small delay. Okay, this is what we call the threshold. There is advantages and also disadvantages, and we have to know what performance that we want to achieve in that circuit. Okay, if the delay is not critical, then we can just consider a high threshold voltage. Okay, so for high threshold voltage, then the standby power dissipations will be lower. The delay will be high. Okay, high delay. Okay, now you can know the threshold voltage can have different influence in delay and power dissipations. Okay, I will discuss furthermore in part 2. Okay, reducing the threshold voltage from 0.8 volt to 0.5 to 0.2 volt can improve the delay at VDD equals to 2 volt by a factor of 2. The positive influence of threshold voltage reductions upon propagation's delay is especially pronounced at low power supplies voltages or VDD below 2 volt. However, that using low VT transistor, it raises significant concern about noise margins and sub-threshold conductions. Smaller threshold voltage leads to smaller noise margin for the CMOS logic gates. The sub-threshold conductions current also set a severe limitations against reducing the threshold voltage. For threshold voltage smaller than 0.2 volt, linkage due to such threshold conductions in standby, where the gate is not switching, may become a very significant component of the overall power consumptions. In addition, propagation delays become more sensitive to process-related fluctuations of the threshold voltage. Okay, so from this slide, we can further conclude the threshold voltage can also leads to different noise margin. Okay, so smaller threshold voltage will have a smaller noise margin. Okay, this is another parameter we should consider as well when we want to apply small threshold voltage in a CMOS logic circuit. Okay, not only power dissipations and delay, noise margin as well. Okay, and also when the threshold voltage use is small, okay, the sub-threshold conductions currents will will be significant. Okay, will be significant. Okay, just now I say that there is the power consumptions called as standby power consumptions. Okay, standby power consumption is one of the power consumptions that is okay, standby power consumption is a power consumptions that occur when the gate is not switching. Okay, remember we still have other power consumptions, the static power consumption due to linkage, and then due to what else? Okay, have to refer back. Okay, there are two causes. Okay, so one of the power consumptions that contribute to the total is the standby power consumptions. This standby power consumption is occur when the gate is not switching, already stated here. Okay, and it is caused by the subthreshold conductions. Okay, subthreshold conductions already mentioned to you before in previous class. Okay, is also in this note. Okay, you can refer back. It's about the linkage power consumptions. Okay, so this one also will become significant, okay, if the threshold voltage is very small. Okay, so I will continue with another slide. Okay, all the parameters that I mentioned to you just now, okay, you have to try to understand. Okay, all these are related, okay, and uh, this is an important topic. Okay, you have to make sure that you do the revisions. Okay, so now I goes to the part 2. Okay, this is the part 2. Okay, in part 2, I will cover on the circuit design technique. Okay, how to overcome the linkage and high standby power dissipations. Okay, with a low threshold voltage circuit. Okay, so just now I mentioned about what is the threshold of applying a low threshold voltage in the circuit. Okay, uh, and the concept that I explained to you just now, okay, all the parameters with its relationship, okay, are also applied here. Okay, apply in this circuit design technique. Okay, today you will learn 3 circuit design. Okay, the 3 circuit design are used to overcome the linkage and high standby power dissipations. They are called as a variable threshold CMOS. Okay, and in short, it is a VT CMOS. Okay, VT stands for variable threshold, and the multiple threshold CMOS. Okay, it is defined in a short form as MT CMOS. Okay, and another circuit called as adiabatic. Okay, adiabatic logic circuit. Okay, first I will introduce to you the first circuit design, variable threshold CMOS circuit. Okay, the examples that I will use is also based on a CMOS circuit. Okay, most the circuit are inverter. Okay, CMOS inverter, and the circuit is integrated with another system. Okay, the system is used to overcome the linkage. Okay, and the high power standby power dissipation. Okay, yes, it is a standby power dissipations. Okay, when the low threshold voltage is applied. Okay, so in this slide, it stated that using a low supplies voltage VDD and a low threshold voltage VT in CMOS logic circuit, okay, is an efficient method for reducing the overall power consumptions while maintaining high speed performance. Yet, designing a CMOS logic gate entirely with low threshold voltage transistor will inevitably lead to increased subthreshold linkage and consequently to higher standby power dissipations when the output is not switching. One possible way to overcome this problem is to adjust the threshold voltages of the transistor in order to avoid linkage in the standby mode by changing the substrate bias. The threshold voltage of an MOS transistor is a function of its source to substrate voltage, as we have already discussed in chapter 3. Okay, this chapter 3 is not the chapter 3 in the notes that I give to you. Okay, this is a book, chapter 3 in a book. Okay. Okay, this is a figure 11.11 for variable threshold CMOS. Okay, you see on this figure, it is an inverter. Okay, it is an inverter and with PMOS and NMOS. Okay, the diagram here, there is small corrections here. Okay, there is a bubble here. Okay, this is a PMOS. Okay, this is PMOS. Okay. There is no bubble here, so it looks like an NMOS, but actually it is a PMOS. Okay, since the threshold voltage here give is PMOS, okay, so this one, all of you, you must know, okay, this is a PMOS actually. Okay, this circuit, as you see, it is an inverter, CMOS inverter, okay, and the threshold voltage, okay, can be adjusted, okay, in active mode and in standby mode. Okay, the threshold voltage for PMOS, you see there are two thresholds. Okay, one threshold minus 0.2 volt is in active mode. Okay, and another threshold voltage, negative 0.6 volt is to use in standby mode. And for the NMOS, the threshold voltage is also the same. Okay, the magnitude is the same with the threshold voltage of the PMOS. Okay, except that for NMOS, the magnitude and the sign here is positive. Okay, and you see here, there is another circuit we call as a substrate bias control circuit. Okay, just now mentions that the threshold voltage can be adjusted by adjusting the substrate bias. Okay, this substrate bias circuit are connected to the substrate of the MOS transistor. Okay, this is the substrate terminal. Okay, this is also substrate terminal. Okay, they are connected to the substrate. Okay, and there is a substrate voltage. Okay, here is the VBP. Okay, VB here is the substrate voltage. Or I should mention it as substrate bias voltage. Okay, I directly refer here. Okay, substrate bias voltage. There are two as well. Two substrate bias voltage. That is for PMOS and NMOS respectively. Okay, the value are different. For the PMOS, the subtract bias voltage are positive. Okay, they are positive in active and standby mode. Okay, and also the subtract bias voltage, the NMOS has also different values in active mode and standby mode. Okay, how to control the system? Okay, this is a circuit. Okay, how it is functions. Okay, it will describe. Okay, not very detailed. Okay, but it shows you how this substrate bias control circuit is used to overcome the linkage and high standby power dissipations. Okay, the statements here. Okay, here the figure, it shows that the threshold voltage of NMOS and PMOS transistor are increased by adjusting the substrate bias voltage in order to reduce the subthreshold linkage current in the standby mode. Okay, so it already mentions in the previous slide. Okay, the threshold voltage can be adjusted. Okay, if we want to increase the threshold voltage, we have to use this method. Okay, by integrating the substrate bias control circuit to adjust the substrate bias voltage, then the threshold voltage of the transistor can be increased. Okay, low threshold voltage will cause a significant linkage. Okay, in this circuit as shown in figure 11.11, the transistors are designed inherently with a low threshold voltage, and the substrate bias voltages of NMOS and PMOS transistor are generated by a variable substrate bias control circuit when the circuit is operating in its active mode. The substrate bias voltage of the NMOS transistor is 0. Okay, 0 volt is the NMOS transistor. Okay, and the substrate bias voltage of the PMOS transistor is equivalent to VDD. Okay, thus the inverter transistor do not experience any backgate bias effect. Okay, so this one we can refer back to the diagram. Okay, this diagram, it explains when the circuit is in active mode. Okay, circuit is in active mode, the substrate bias voltage level. Okay, for NMOS it is 0 volt, and for PMOS it is 2 volt. This 2 volt is the same voltage level with the power supplies VDD. The circuit operates with low VDD and low threshold voltage, benefiting from both low power dissipations due to low supplies voltage and high switching speed due to low threshold voltage. When the inverter circuit is in the standby mode, okay, now I'm talking about the standby mode. Okay, however, the substrate bias control circuit generates a lower substrate bias voltage for the NMOS transistor and a higher substrate bias voltage for the PMOS transistor. Okay, refer to this diagram, you see in standby mode, the substrate bias voltage for PMOS and NMOS, they are different. One is higher, one is lower. Okay, the substrate bias voltage is to adjust the threshold voltage so that it is not very low. Okay, as a result, the magnitude of the threshold voltage of the PMOS and NMOS both increase in the standby mode due to the backgate bias effect. Okay, so in standby mode, okay, this is standby mode. You see the threshold voltage in standby mode is higher than that of the threshold voltage in active mode. Okay, this higher threshold voltage is actually after adjusted through the circuit. Okay. This circuit adjusts the substrate bias voltage, okay, in order to achieve a higher threshold voltage. Since the subthreshold linkage currents drop exponentially with increasing threshold voltage, the linkage power dissipations in the standby mode can be significantly reduced with this technique. The VT-CMOS technique can also be used to automatically control the threshold voltages of the transistor in order to reduce linkage current and to compensate for process-related fluctuations of the threshold voltages. This approach is also called as the self-adjusting threshold voltage scheme. Okay, VT-CMOS has another name. Okay, its name is called as a name. Okay, is the is a method. Okay, it is the method of the CMOS. Okay, it is called as a self-adjusting threshold voltage scheme. The variable threshold CMOS circuit design techniques are very effective for reducing the subthreshold linkage current and for controlling threshold voltage value in low VDD and low VT applications. However, this technique usually require twin well or triple well CMOS technology in order to apply different substrate bias voltages to different part of the chip. Okay, also separate power pins might be required if the substrate bias voltage level are not generated on chip. The additional area occupied by the substrate bias control circuitry is usually negligible compared to the overall chip area. Okay, so based on the statements here given, it shows that the VT-CMOS is quite effective, okay, to reduce the linkage current, okay, and then it can use to control the threshold voltage, okay. But these techniques require this, okay. This one is a technique of how the CMOS technology is fabricated with different substrate bias voltages. Okay, this is the maybe can say is a drawback. Okay, the technology it is used, okay, will be more advanced. Okay. Okay, another figure here is given. Okay, it shows a digital system, a chip. Okay, a chip with a VT-CMOS. Okay, this figure 11.12 shows the block diagram of a typical low power chip with low internal supply voltage and the threshold voltage control. Okay, this is a block diagram, okay, of a chip. Okay, and there is an input output circuit, signal level converter, DC-DC voltage converter, internal circuit with low threshold voltage, and threshold voltage control. Okay, and here you can see that the VT-CMOS is this part. Okay, it is this part. This internal circuit is controlled by this threshold voltage control. Okay, the threshold voltage can be controlled using the technique learned just now. Okay, what is input output circuit and DC voltage converter? What is the functions in the chip? Okay, for the input output circuit, okay, it is usually operate with a higher external supply voltage in order to increase the noise margin and to enable communications with the periphery devices. And on-chip DC to DC voltage converter generate the low internal supplies voltage VDD, which is used by the internal circuitry. Okay, now I refer back to the figure. Okay, this figure, if follow the statements given just now, okay, it means that this input output circuit, this input output circuit, okay, the supplies voltage used is higher. Okay, and here this part, the supplies voltage used is smaller. Okay, supply voltage used is smaller. Okay, the supplies voltage can be controlled and adjusted through the DC-DC voltage converter. Okay, this internal circuit cannot supply with high VDD. Okay, it can only supply with low VDD. So a DC-DC voltage converter is used, okay, to regulate the threshold voltage. Sorry, not threshold voltage, to regulate the supplies voltage. Two signal swing converter are used to reduce the voltage swing of the incoming input signals and to increase the voltage swing of the outgoing output signals respectively. Okay, the signal level swing, okay, this one swing converter is actually this one. Okay, these two. The internal voltage for low voltage circuitry can be designed using VT-CMOS technique, where the threshold voltage control unit adjusts the substrate bias in order to suppress the linkage current. Okay, there is an internal low voltage circuitry, just now already showed to you. Okay, it is operate with low threshold voltage. Okay, and it is designed using the VT-CMOS technique with the threshold voltage control system. Okay, so that is all about the VT-CMOS. Okay, the very fundamental theory about VT-CMOS and how VT-CMOS can use to overcome the linkage and standby power dissipations. Okay, now I will go to another circuit design called as empty CMOS. Okay, let me see what is the time now. Okay, I see now it's already 3 o'clock. Okay, I will take a break now. Okay, after 10 minutes, then I will continue with this. Okay, I will continue my lecture now. Okay, there is another circuit design. Also, we can call it as a technique. Okay, that is empty CMOS. Okay, it can be applied for reducing the linkage current in low voltage circuit in the standby mode. Okay, this circuit is based on using two different types of transistor, both NMOS and PMOS, with two different threshold voltages in the circuit. Okay, here low threshold voltage transistor are typically used to design the logic gates where switching speed is essential, whereas high threshold voltage transistors are used to effectively isolate the logic gates in standby and to prevent linkage dissipations. The generic circuit structures of the empty CMOS logic gate is as shown in 11.13. Alright, so this is the figure 11.13. Is a CMOS inverter with a PMOS and NMOS and a CMOS logic. Okay, the structures here is quite similar to the CMOS inverter. Okay, except that the PMOS and NMOS, as you see, they are controlled with high threshold voltage. Okay, both are controlled with high threshold voltage, and there is a CMOS logic block. This CMOS logic block is controlled with a low threshold voltage. Okay, and this circuit is also operate in two mode. One is active mode and another one is standby mode. Okay, given here in the active mode, the high threshold voltage transistor are turned on, and the logic gates consisting of low threshold voltage transistor can operate with low switching power dissipations and small propagations delay. Okay, so the statements here describe when this circuit is in active mode. Okay, all of these transistor are operated. Okay, are operated. The PMOS and NMOS. Okay, when it is in active mode, okay, it will turn on. Okay, and this CMOS logic block with low threshold voltage will also operate. Since this CMOS logic block is with low threshold voltage, so means that it can switch very fast, okay, because of the low threshold voltage applied. Okay, the switching power dissipations will be low, and the propagations delay here mentioned is also small. Okay, and the circuit when it is in standby mode, the high threshold voltage transistor are turned off, and the conduction path for any subthreshold linkage current that may originate from the internal low threshold voltage circuitry are effectively cut off. Okay, this is when, okay, the statements here is for the circuit when it is in standby mode. This CMOS logic with low threshold voltage, okay, it will be cut off when in standby mode. Okay, two different mode, the transistor that are operated, okay, are also different. Okay, for the PMOS and NMOS with high threshold voltage, okay, it is to prevent the subthreshold linkage in standby mode. Okay, and the CMOS logic circuit with low threshold voltage, it is with high speed operations and low power consumptions. Okay, the for this case, the power consumption is low when the low threshold voltage is applied. Okay, but if this circuit is not a empty CMOS, then the power consumptions will be high from the low threshold voltage. Okay, the power consumptions here is the standby power consumptions that is caused by the linkage current. Okay, but for this is a empty CMOS, so the power consumptions here is low. Okay, it is low even though a low threshold voltage is applied. Figure 11.14 shows a simple D-latch circuit design with the empty CMOS technique. Okay, so you see the figure 11.14 here. It is very similar to the structures of the empty CMOS that I show you just now. Okay, with the PMOS that is connected to the input called standby. Okay, and also the NMOS. Okay, this NMOS, the input is the inverted standby. Okay, means that if the input is 0 or the voltage level is low, then this PMOS will operate. Okay, and this NMOS, if it is low, it is this NMOS will also operate. Okay, because you see this is 0, right? This is 0 or low voltage, and this is low voltage. Standby is low voltage, but there is a bar here, so it become 1. Means that both NMOS, PMOS and NMOS will operate. Okay, will turn on. Okay, when they are in active mode. Okay, but in standby mode they will turn off. Okay, this is according to this operations given. Okay, and then the CMOS logic block. This is the CMOS logic block. Okay, the internal architectures of this CMOS logic block looks like this. Okay, this is a pass transistor. Okay, this one I covered before, but I didn't cover in depth. Okay, this is just for you to know. Okay, uh, the structures of a CMOS logic blocks in the for this one. Okay, this is called as a D-latch. Okay, this is called as D-latch. Okay, this is a circuit that use the empty CMOS technique, so we can call it as a low power D-latch. Okay, as you see here. Okay, advantage and disadvantage. Okay, this is about the advantages and disadvantages of using empty CMOS technique. Okay, empty CMOS technique conceptually is easier to use and apply compared to the VT CMOS. Okay, it doesn't like a VT CMOS technique. Okay, why it is not like? Because VT CMOS technique require a sophisticated substrate bias control mechanism. Okay, this is the bias control system circuit that I show you just now. Okay, in empty CMOS, this circuit is not required. Okay, and empty CMOS, uh, it has some significance, the difference. Okay, uh, okay, the fabrications method, okay, to use for this empty CMOS, okay, is a slightly different than the VT CMOS. Okay, here state that the only significant process related overhead of empty CMOS circuit is the fabrications of MOS transistor with different threshold voltages on the same chip. Okay, here is running. I am not sure whether you can hear me clearly or not. Can you hear me? Can three of you hear me? No, very soft. Oh, okay. Uh, okay, I try to increase my voice. Hmm. Okay, so these are all the advantages. For disadvantages, there is one disadvantages. The presence of the series connected standby transistor increases the overall circuit area and also add extra parasitic capacitance. Okay, this is about the standby transistor. There are 1 PMOS and NMOS. It will add the parasitic capacitance. Okay, while both the VT CMOS and MT CMOS circuit technique can be very effective in designing low power and low voltage logic gates, they may not be used as a universal solutions to low power CMOS logic design. Okay, um, so these two techniques you have learned, okay, they are effective in designing a low power logic gates, okay, but is not the solutions for all, okay, for all the logic circuit, okay, only for certain logic gates. Okay, that is all about the circuit design, the two circuit design, the operations are mentioned. Okay, now I goes to the estimations and optimizations of switching activity. Okay, so uh, when we talk about switching activity, okay, it should relates to the power dissipations. Okay, all this while you learn about power dissipations and power dissipations. There is a switching power dissipations. Okay, that switching power dissipations we can actually control by controlling the switching activity. In low power design, beside minimizing power dissipations in CMOS circuit by supply voltage scaling, more approach is to reduce the switching activity and the amount of the switch capacitance to the minimum level required to perform a given task. Okay, so this one back to the formula again. The power dissipations for dynamic power dissipation. Okay, there is a formula. Okay, this formula, if you can recall, not only the supply voltage, the clock frequency and the capacitance, this is the load capacitance, okay, will uh, increase the power dissipation if they are high. Okay, and here there is a factor. This factor is called as activity factor. Okay, there is a formula. Okay, you can refer back, okay, the notes given. Okay, so this is about the switching activity. Okay, this is about the switching activity. We can reduce the switching activity to minimize the power dissipations. The measure to accomplish this goal can range from optimizations of algorithm to logic design, and finally to physical mask design. Okay, for these reductions of switching activity, can you all hear me? Yes. Huh? Oh, okay. Okay, for reductions of switching activity, the reductions method, okay, are at different level. Okay, the optimizations at different level, and then the reductions method here given by algorithmic optimizations. Okay, optimizations, architectures optimizations, proper use of logic topology, or by circuit level optimizations. Okay, all these are the method that can use to reduce the switching activity. Okay, what is the algorithmic optimizations and also architectural optimization and circuit level optimizations? Some of the reductions method will be discussed. Okay, the algorithmic optimizations will be discussed, and the proper use of logic topology. Not all will be discussed, but only two. Okay, two method will be discussed further. So you can know what is it about and then how the optimizations can be done to reduce the switching activity. Okay, the measure that can be applied to optimize the switching probabilities and hence the dynamic power consumptions. Okay, first measure is the algorithmic optimization. It depends heavily on the applications and on the characteristics of the data, such as dynamic range, correlations, and statistics of data transmissions. About algorithmic optimizations, it means that it uses algorithms to do the optimization, optimize the switching. Okay. Some of the algorithm used can apply for specific applications, such as the DSP. This is about digital system processing. Okay, another algorithm. Okay, for examples, a proper vector quantizations algorithm can choose for minimum switching activity. Okay, there are many algorithms out there. Okay, some algorithms can be used for these applications. Okay, and also depends on what applications we must select the correct algorithm. Okay, for this purpose. The numbers of memory access, the number of multiplications, and the numbers of addition can be reduced by about a factors of 30 if differential tree search algorithm is used. Okay, here different algorithms name is given here. Okay, we don't know what is the algorithm. Okay, never mind. So this is just for your knowledge. Okay, you never learned this algorithm before. Okay, this only to show you there are different algorithm and then they can perform. Okay, to reduce and optimize the switching activity. Okay, next is the representations of data. Okay, the representations of data can have a significant impact on switching activity at the system level. For example, the use of gray coding or sign magnitude representations instead of the conventional two complements representations for sign data. The switching activity can be reduced by using the sign magnitude representations in applications where the data sign change are frequent. Okay, so for this one, okay, it is another method, okay, that we can control the switching activity. Okay, these are sign magnitude representations. Also, we are not familiar. Okay, this one have to study further. Okay, we have to go to look in the books and only we know what is it about. Okay, but for this one, uh, this is one of the method. Okay, just for your informations. The amounts of switch capacitance plays a significant role in the dynamic power dissipations of the circuit. Hence, reductions of this parasitic capacitance is a major goal for low power design of digital integrated circuit. Various techniques at the system level, circuit level, and physical design level can be used for reductions. At the system level measure, the technique that is to use is to limit the use of shared resources. Okay, what is meant by this? Later, a diagram will be shown to you to illustrate the technique. At circuit level measure, this measure use different type of logic style to implement a digital circuit. It will affect the output load capacitance of the circuit. At the physical design level, or we can also call as the mass level, the measure is to keep the transistor at minimum dimensions whenever possible and feasible, thereby minimizing the parasitic capacitance. Okay, this method, all of you know. Okay, the larger the size of the transistor with the drain and source region, then the parasitic capacitance will be larger. Okay, so the size of the transistor with drain and source region must be made as small as possible. Okay, the parasitic gate and diffusion capacitance of most transistors in the circuit typically constitute a significant amount of the total capacitance in a combinational logic circuit. Okay, just now mentions that the parasitic capacitance will contribute to high power dissipations. Okay, so one of the method at the physical design level is to reduce the dimensions of the transistor. Okay, okay, just now I mentioned the three measures at different level: system level, circuit level, and the physical design level. Okay, now I will describe the measure one by one. Okay, uh, each level for each level. Okay, now is the system level. At system level, just now mentions that at system level, it can limit the use of a shared resources. Okay, what is mean by that? Okay, so you can see in this slide, there are a figure. In figure 11.25, you see there is a two diagram here. This diagram shows a single global bus. Okay, okay, maybe I will just directly state this out. Okay, the diagram in part A, using a single global bus structures for connecting a large numbers of modules on chip result in large bus capacitance and large dynamic power dissipations. Okay, so this refer to this diagram. Okay, the single global bus, this is the single global bus. Okay, and this is module. Okay, imagine that this is the system on chip. Okay, this is a system on chip with module, single global bus. Okay, and this structure with only one global bus will cause a large bus capacitance. Okay, and it also cause large dynamic power dissipations. These large dynamic power dissipations can be caused from the large capacitance. Okay, so to overcome the high power dissipations, okay, another uh, technique, okay, we can limit the share resources. Okay, means that we can use more than one global bus. Okay, in part B, you see here, okay, the smaller local buses, okay, reduce the amount of switch capacitance at the expense of additional chip area. Okay, all this line, this is local bus. Okay, local buses, this is also local bus. This is local bus. Okay, when we count all, then we call them as buses. Okay, here there is a module as well. Okay, this is module. Okay, with the use of local buses, the switch capacitance can reduce. Okay, can reduce, but the chip area that it is occupied is larger. Okay, this one is the negative side. Okay, when the smaller local buses are used. Okay, the statements given here uh, is the one that I explained just now. Okay, here mentions that if a single bus is connected to all module in figure 11.25a, it result in a large bus capacitance due to the large numbers of drivers and receivers sharing the same transmissions medium and the parasitic capacitance of the long bus line. Okay, so this is about a single global bus used to share with many modules, okay, and drivers. Okay, and alternatively, okay, this is about the part B. The global bus structures can be partitions into a numbers of smaller dedicated local buses to handle the data transmissions between neighboring module. In figure 11.2b, 25b, the switch capacitance during each bus access is significantly reduced, although multiple buses may increase the overall routing area on the chip. Okay, this is referred to this one. Okay, all already explained just now. Okay, okay, another measure at circuit level. Okay, just now the measure mentions here is to use different type of logic type to implement a digital circuit at circuit level. Okay, the logic style that is used will affect the output load capacitance. Okay, so here we'll mention about that. Okay, the capacitance. Okay, since just now mentions that the capacitance will be affected. Okay, so it will relate with the capacitance. The capacitance is a function of the numbers of transistors that are required to implement a given functions. One approach to reduce the load capacitance is to use transfer gates. Transfer gate is the pass transistor logic instead of conventional CMOS logic gates to implement logic functions. Okay, on the pass transistor logic, let me see, is there any diagram? No diagram here. Okay, pass transistor logic, okay, is another type of a transistor called as a pass transistor. Just now I show you already. Okay, it is used instead of using this PMOS and NMOS in conventional CMOS logic gates. Okay, pass gate logic design is attractive since fewer transistors are required for certain functions such as exclusive OR and the exclusive NOR gate. Therefore, this design styles has emerged as a promising alternative to conventional CMOS for low power design. Still, a number of important issues must be considered for pass gate logic. It uses to achieve low power dissipations. Okay, it must be carefully considered, and the choice of logic design style must ultimately be based on a detailed comparisons of all design aspects such as silicon area, overall delay, as well as the switching power dissipations. Okay, this slide is just describe about the measure taken at circuit level, okay, with different logic style. Okay, the logic styles here is applied based on the use of the pass transistor logic. Okay, now I goes to the next one. Next one is about the measure at physical design level. Designing a logic gates with minimum size transistor certainly affects the dynamic performance of the circuit, especially in circuit driven a large extrinsic capacitive load. For example, a large fan-out or routing capacitance, the transistor must be designed with larger dimensions. Yet in many cases where the load capacitance of a gate is mainly intrinsic, the transistor size can be kept at a minimum. Okay, again, this mentions about the dimensions of the transistor. Okay, the capacitance can be reduced through adjusting the size of a transistor. Okay, and then depends on the type of the circuit. If the circuit is driving a large extrinsic capacitive load, then the transistor must make it with large dimensions. Okay, different transistor size have to use in different circuit. okay, for different applications. Okay, another circuit technique. Okay, this is the third circuit technique. We call it as a adiabatic logic circuit. Okay, this adiabatic logic circuit is different. Is quite different than the MT CMOS and VT CMOS. Okay, it is not about controlling the threshold voltage of the circuit. Okay, it is about to recycle the energy. Okay, power dissipation is about the dissipated heat. Okay, and also about the energy. Okay, so for adiabatic logic circuit, okay, it is about recycle the energy drop. Okay, so according to the statement in the slide here, okay, to reduce the dissipation, the circuit designer can minimize the switching event, decrease the node capacitance, reduce the voltage swing, or apply a combination of this method. Yet, in all these cases, the energy draw from the power supply is used only once before being dissipated. To increase the energy efficiency of logic circuit, other measure can be introduced for recycling the energy drawn from the power supply. A novel class of logic circuit called adiabatic logic offer the possibilities of further reducing the energy dissipated during switching event and the possibilities of recycling or reusing some of the energy drawn from the power supply. To accomplish the circuit topology and the operations principles have to be modified. Okay, sometimes the modifications will be drastical. The amounts of energy recycling achievable using adiabatic techniques is also determined by the fabrication technology, switching speed, and voltage swing. Okay, from the slide here, okay, you can note that the adiabatic techniques is about the method of recycling the energy draw from the power supply. Okay, and the amounts of energy draw is determined by the fabrications technology, switching speed, and voltage swing. Okay, the terms here, the adiabatic. Okay, this is adiabatic logic technique. The terms of adiabatics here is given. Okay, okay, the terms here, as you see, it describes thermodynamic processes that have no energy exchange with the environment, and therefore no energy loss in the form of dissipated heat. Various techniques will be explored to minimize the energy loss or heat dissipations during charge transfer event. Fully adiabatic operations of a circuit is an ideal conditions which may only be approached asymptotically as the switching process is slowed down. In practical cases, energy dissipation associated with a charge transfer event is usually composed of an adiabatic components and a non-adiabatic components. Therefore, reducing all energy loss to zero may not be possible regardless of the switching speed. Okay, I think if you read it carefully, you will be able to understand what is meant by the statements here. Okay, this logic circuit, since it is used to recycle the energy drawn from the power supply, and the energy loss can be minimized, but the energy loss, ideally, it can be reduced to zero, but in reality, it will not be able to reduce to zero. Okay. Okay. For this and adiabatic logic circuit, a simple circuit configurations is given. Okay, they are used for adiabatic switching. Okay, other circuit topology are also possible, but the overall terms of energy recycling should be enforced. Okay, regardless of specific circuit configurations. Okay, later there is circuit configurations will be shown. Okay, this circuit configurations is one of the examples of adiabatic logic circuit, and other circuit configuration is also possible. Okay, but the configurations must be made to have these energy recycling functions. Okay, in figure 12.27, okay, figure 12.27, the circuit called as a adiabatic amplifier circuit. It is used to drive the capacitive load. Okay, so this is the figure. Okay, it is called as adiabatic amplifier circuit. Okay, this circuit has input and output. The input is X, output is Y. Okay, and then the middle here, the middle part here, called as the CMOS transmission gate. Okay, the structures of the circuit, as you see, okay, it consists of two CMOS transmission gate and two NMOS clamp transistors. Both the input X and the output Y are dual rail encoded, which means that the inverse of both signals are also available to control the CMOS transmission gate. Okay, so the figure as you see here, okay, this is the CMOS transmission gate. There are two, okay, and these transmission gates are controlled by the input signal X. Okay, one is X, another one is inverted X, and the NMOS, this is the NMOS transistor. NMOS transistor here is called as the clamp transistor. Okay, the operations of this circuit is as such. When the input signal X is set to a valid value, one of the two transmission gates become transparent. Next, the amplifier is energized by applying a slow voltage ramp, VA, rising from zeros to VDD. The load capacitance at one of the two complementary output is adiabatically charged to VDD through the transmission gate, while the other output nodes remain clamped to ground potential. When the charging process is completed, the output signal pair is valid and can be used as input to other similar circuit. Okay, the circuit is de-energized by ramping the voltage VA back to zero. Thus, the energy that was stored in the output load capacitor is retrieved by the power supply. Okay, based on the statements here, okay, it mentions the process of the circuit. Okay, the process here involve the charging process, okay, and the discharging process. Okay, the output capacitance here is mentioned. Okay, it refers to this CY. Okay, CY is the load capacitance. Okay, for this one, you don't have to memorize. You just understand. Okay, you can try to understand, but if you cannot try to understand, it's okay. But this is just to show you how adiabatic logic circuit looks like. Figure 11.28. Okay, I just see the times. I only have 5 minutes left. Okay, I have how many slides? Okay, I have 3 more slides. Okay, I hope I can finish all today since I only have 3 slides. Okay, figure 11.28 shows a general circuit topology for conventional CMOS logic gates and adiabatics counterparts. Okay, the figure 11.28 is actually this 11.28. Okay, this circuit topology is a conventional CMOS logic circuit. Okay, with pull up and pull down network, and also output capacitance at the output. Okay, this one is common. Okay, we call it conventional CMOS logic gate. Okay, and then there is another circuit topology. This is another one. Okay, which we call it as adiabatic logic gates that implementing the same functions. Okay, means that these two circuits they can perform the same functions except that the structures here you see is different. Okay, this circuit we call adiabatic logic circuit, and the output capacitance, there are two output capacitance. Okay, the input is still the same. Okay, and also the process are still the same. Okay, just a slight change in the structure. To convert a conventional CMOS logic gates into an adiabatic gate, the pull-up network and pull-down network must be replaced with complementary transmissions gate network. Okay, complementary transmissions gate network means the gate that I showed just now. Okay, this is the transmissions gate. Okay, so if you refer back to this circuit, here the networks here, okay, the gate that used is a transmissions gate. The gate network, transmissions gate network, in short it is called as a T gate network. Okay, it implementing the pull out functions. This T network that implements the pull out function is used to drive the true output of the adiabatic gates, while the T gate network implementing the pull down functions drive the complementary output nodes. All input should also be available in complementary form. Both network in the adiabatic logic circuit are used to charge up as well as charge down the output capacitance, which ensures that the energy stored at the output node can be retrieved by the power supply at the end of each cycle. To allow adiabatic operations, the DC voltage source of the original circuit must be replaced by a pulse power supply with ramp voltage output. Note that the circuit modifications which are necessary to convert a conventional CMOS logic circuit into an adiabatic logic circuit increases the device count by a factor of 2 or even more. And in general, the reductions of energy dissipations come at the cost of slower switching speed, and it is a trade-off in all adiabatic methods. Okay, so from this slide, the adiabatic logic circuit are described. Okay, with is a process. Okay, there is a charge up and charge down process as well. Okay, and then the voltage source used is not a DC voltage source, it is a pulse power supply. Okay, so these are all about the adiabatic logic circuit. Okay. Okay, another figure is shown here. Okay, is given in your notes. Okay, it is to show another examples of a circuit diagram of an adiabatic logic gate. Okay, this adiabatic logic gate is a CMOS NAND or the NAND. This is AND gate. Okay, AND gate and also NAND gate. Okay, so here you see this is all the past transmissions gates. Okay, this is the supposed to be the pull out network, and this is the pull down network. Okay, In conventional circuit, they are called as pull out and pull down network. But here, in adiabatic, okay, we don't call it pull out and pull down. Okay, the past transmissions get replaced, all this replace the pull out and pull down network. Okay, so I think that is all about the adiabatic logic gates. I cover only the very fundamentals theory, okay, on this circuit technique. Okay, as a summary, VT CMOS and MT CMOS are used to overcome the linkage current and high standby power dissipations due to low threshold voltage applied in circuit. Approaches of reducing power dissipations involve the reductions of switching activity, reductions of swing capacitance at system level, circuit level, and physical design level. Okay, not only that, there are also other more approaches. Okay, other more approaches are the approaches that I have mentioned just now. Okay, the reductions can be from the reductions of power supply and the use of appropriate circuit technique. Okay, adiabatic logic circuit can offer significant reductions of energy dissipations, but usually at the expense of switching time. Therefore, such adiabatic logic circuit can be best utilized in cases where delay is not critical. Moreover, the realizations of unconventional power supplies needed in adiabatic circuit configurations typically result in an overhead both in terms of both overall energy dissipations and silicon area. This issue should be carefully considered when adiabatic logic is used as a method for low power design. Okay, so this is the summaries for the topic for this chapter 10. Okay, so I will stop here. Okay, I see that the time now the time is 4 o'clock. Okay, I think that okay, now think no issue anymore on attendance. If you have no other questions, then we can dismiss class now. Okay, thank you.